Okay, so we've introduced Gaussian processes, and now I want to give you a slightly different view or a different way of thinking about these things in terms of eigenvectors and eigenvalues. So if you recall, you can think about a multivariate normal as kind of, think about a multivariate normal as being a random combination of the eigenvectors of the covariance matrix, where the eigenvectors are being weighted by their eigenvalues. So eigenvectors that have a big eigenvalue, those directions of the multivariate normal tend to be bigger, so have a higher, stronger in those directions, and where the eigenvalues are small or even zero, then the multivariate normal has small or zero variation in those directions. So that was something we looked at last time. So you can think Gaussian processes in the same way, but now the eigenvectors are defined everywhere in space instead of being they're also infinite dimensional object. They're really eigenfunctions. So let's, that's in this GP example here. Actually, this example starts off just by simulating some Gaussian processes with different covariance kernels, which I put into a different vignette. So you've kind of seen this before. These are all squared exponential kernels, and these are the Ornstein-Uhlenbeck. Remember, these are the like more smoother Gaussian processes, and these are the Ornstein-Uhlenbeck tends to be less smooth, and then there's the Matern that tends to be somewhere in between. So here, instead of putting points, I've kind of joined them up, although strictly speaking, I've only generated them at a finite number of locations and then joined them up. But just to give you a kind of idea that they're conceptually kind of continuous, but it's a bit misleading because you haven't actually observed them everywhere. But and then it's the end of this vignette here that I look at the eigen decomposition. So remembering that every covariance matrix can be written in this form, like this, so as a eigen decomposition, and then we can think of the multivariate normal as having random weights on the v's. Let's call them z, random weights zi on vi, where zi is normal 0 lambda I. Or if you prefer, you can have them to be square root of lambda I, zi, vi. And so so you can write it as the sum over I over vi square root of lambda I vi, right? Then, and the zi's are now normal 0, 1 iid, then that implies that x is multivariate normal 0 sigma, where sigma equals v lambda v transpose, right? That's what we did last time. Okay, so we're just applying that same idea here to look at what the eigenvectors, quotes, eigenvectors of these kernels are. So I've done everything in discrete space because I can't work with infinite dimensional objects, but conceptually, you could imagine taking the limit as we increase the number of these discrete points, right? So I'm doing everything discretely because I can't on a computer work with the infinite dimensional object. But so here are the eigenvectors of the discrete, but still kind of high dimensional covariance matrix that led to this, that I got out of the squared exponential kernel, right? So that's the one that led to these kinds of plots, these very smooth Gaussian process realizations. This is also squared exponential kernel. So here are the eigenvectors. So the idea here, actually, so the first eigenvector, or at least is the black one, and then the red one. So what you can see here is that the black one's kind of the low frequency, and the red one's higher frequency, and then it's green, and then blue. So these are kind of increasing frequency. Yeah. So the idea is you can think of these curves, not these ones here, as each being a random combination of those eigenvectors. Well, okay, not just the first 5 eigenvectors or however many I showed, but all of them conceptually. But what happens is the eigenvalues decay, and as we'll see in a minute, the eigenvalues for the squared exponential decay quite quickly, so that the shapes of these curves are dominated, the weights are mostly on those first few eigenvectors, the lowish frequency ones. And that's why these curves look kind of smoothish, right? Because most of the weight, essentially they're kind of a linear combination of these eigenvectors. What's kind of maybe a bit surprising at first is that if we do the same thing for the Ornstein-Uhlenbeck kernel, the eigenvectors look very similar. I mean, there's a, the sign here is, you can take a plus or minus of the sign, they're still eigenvectors, so you can ignore the signs here. I should probably line them up to make them look even more similar, but you can see that just qualitatively, the black one here looks very similar to the black one here, just the negative of it. And similarly, the red one here looks very similar to the red one here, just the negative of it. And the sign's arbitrary. You could switch the sign. So they're not exactly the same, but they're pretty similar. And there's a reason for that, which we'll go into in a moment. But and if you look at the higher order eigenvectors, here's the 30th one, so you can see that they get higher and higher frequency, basically. And so we'll come back to the reason for that, but the eigenvalues behave quite differently. So the eigenvalues for the squared exponential decay much, much faster. That's the black line here relative to the red line here. And if we just look at the small ones, you can see. Sorry, so where's the difference there? So I guess actually I haven't labeled the x-axis properly here, right? Here, I should do that. Okay, so the eigenvalues here are not, there are not 100 of them, I don't think. Well, there are 100 there. Let me just check what's going on there and get back to you. Okay, sorry, I got a little confused. So this plot here is just blowing up a zoom in of this with the y-axis limited. So in this plot, the very biggest eigenvalues are so much bigger than all the others. So it looks like the red line and the black line are maybe very close to one another, very close to 0. But actually, when you look at here, this is just changing that scale. You can see actually the black line goes down to 0, but the red line really doesn't. It stays out there, decays, and doesn't go to 0. So that's the point of this plot, is that the behavior of those very, very small eigenvalues at the right-hand end is very different. And so if you think about what that means, is that you're going to put a lot more weight on components like this in the Ornstein-Uhlenbeck case, because its eigenvalues out there are much bigger. And so that's why you can think of that as, that's why you get pictures like this, because with the Ornstein-Uhlenbeck process, because it tends to put more weight on those high frequency components that are going very, very fast. Pardon me. Whereas with the squared exponential, you put almost 0 weight, well, essentially 0 weight on those high frequency components, which is why you see those high frequency, when I say high frequency components, I mean those eigenvectors that are changing very fast. You hardly ever see any of that. You see no weight on those in the squared exponential kernel. And so you get these smoother curves that don't have those high frequency components. Okay, and actually, yes. Okay, so why are the eigenvectors of these two processes that are pretty different? Why are the eigenvectors so similar? And why do they look so kind of regular? If you look at them, they look kind of very regular. And the answer to that is to do with circulant matrices. So in order to tell you about circulant matrices, and I should say this is maybe an optional topic for you, but I think it's kind of interesting to understand why it happens. So in order to understand about circulant matrices and why they're relevant, instead of, all the math is cleaner if we think about a circle instead of a line. So imagine taking observations on a circle instead of a line, okay, because it kind of gets rid of these edge effects. So, imagine taking equally spaced observations on a circle, in fact. So we've got a circle, we've got observations, temperature varying on a circle maybe, and we're going to observe the temperature at each point around the circle. And we call these 1, 2, 3, 4, 5, etc. Okay, so if you think about it, the distance from 1 to 3 is the same as from 2 to 4, right? And the distance from 1 to 5 is the same as from 2 to 6, etc. So if you think about writing down the distances from 1 to 1 to, sorry, these are locations. The distance from 1 to 1 is 0. The distance from 1 to 2 is, let's say, 1 step. The distance from 1 to 3 is 2 steps. Distance from 1 to 4 is 3 steps. But as long as we, I guess, at the end, if this is n, the distance from 1 to n is 1 step, right? It goes back up again. And then the distance from 1 to 2 is 1 step. The distance from 2 to 3 is, 2 to 2 is 0 steps. 2 to 3 is 1, 2, 3, etc. And 1 to 3 is 2 steps. 2 to 3 is 1, 0, 1, 2. And if you look at these columns, what you can see is that actually what's happening, maybe I should fill in, n to 2 is also 2 steps, right? It wraps around. And I'm defining distance here as just the minimum distance in the circle. So what's happening is that this column here, or maybe I should say this column here, the second one, is just a cyclic shift of the first one. Right? You move this column down, put the 0 there, 1 there, 2 there, 3 there, and you bring the 1 back up to the top, and you get the second column. If you do the same again, you get the third column, and do the same again, you get the fourth column. So this kind of matrix is called a circulant matrix. All right, so a circulant matrix has a very special property. Well, okay, maybe this was the distances. If we have a covariance matrix whose values are a function of the distances, then it will also be circulant, right? So if we collected data on a circle, equally spaced points, and computed the covariance matrix for a stationary isotropic Gaussian process, the covariance matrix would be circulant. Okay. And it wouldn't matter what kernel you used, squared exponential, Ornstein-Uhlenbeck, Matern, they would all be circulant. They wouldn't all be exactly the same circulant matrix, but they would be different circulant matrices, but they'd be circulant. And it turns out, rather remarkably, that the eigenvectors of the n by n circulant matrix of any n by n circulant matrix are the same. I don't mean the eigenvectors are all the same. I mean, it doesn't matter which circulant matrix you look at, you get the same eigenvectors. And they're given by the columns of what's called the discrete Fourier transform matrix. By the columns of the n by n discrete Fourier transform matrix. So they do depend on n. If you change n, you'll get a different circulant matrix, you get a different discrete Fourier transform. But maybe by its name, you can imagine what the discrete Fourier transform matrix looks like it, and well, at least maybe based on pictures we've seen before, the columns kind of vary sinusoidally or trigonometrically, sinusoidally, and of increasing frequency. So the data we looked at were on a line, not a circle, but it turns out that the edge effects that you get at the ends don't make a big difference, and so you can think of like a line as kind of approximating a circle, or a circle approximating a line, if you prefer. So it turns out that that's why the eigenvectors for the Ornstein-Uhlenbeck case and the squared exponential case, the eigenvectors both looked similar to one another and also similar to these kind of sinusoidal things. And it's because of this. The eigenvectors of basically the matrix is kind of similar to a circulant. It's not exactly circulant because we did it on a line, not a circle, but it has a lot of the features of the circulant matrix. And so its eigenvectors are approximately given by the columns of the discrete Fourier transform matrix, which are these signs of increasing frequency. Okay, so that's why. I think that's all I had to say. Let's just, yeah, good. So to summarize, the idea is that you can think of these Gaussian processes having, think of each realization as being a weighted combination, a linear combination of eigenvectors that look like this, where the weights on the eigenvectors depend on what kernel you use. Okay. And yeah, okay, that's good enough.